We are glad that you are here for STEM So What. This is a series that has been going on for 2 years now, started by Dean Bowling, the Dean of the STEM division, and we are excited. This gives us an opportunity to show you, the students, all the practical ways that the things that you are learning in math and science classes actually get used in the real world. And so we have had many different speakers that have come and shared. Of course, tonight, you know, we have Rachel Funk from NASA, and so we're really excited about that. But if you have missed some of the previous ones, there was a paper that had a QR code. We have a LibGuide set up. If you go to the TCC website, look under the LibGuides, all the previous topics are there. And so if you want to see what you've missed, that's a great way to do that. There's also more resources from this talk available there, and future talks will be there as well. Lastly, I do want to introduce our STEM So What committee. I don't know that I told you, my name is Jennifer Anderson. I'm a math instructor here, and I'm on the STEM So What committee. Amanda Wisenant is a math instructor on the STEM So What committee. Right here we have Dr. Jodka, biology instructor on our STEM So What committee. Dr. Elaine Coleman, also of biology. Sarah Martin, who makes sure that you have food. So we are so grateful for her. And then Dr. Archie Wilmer, also of math. Oh, and the wonderful, soon-to-be, Dr. Hobbs, geology. So that is our STEM So What committee. And then finally, I want to introduce Rachel Funk. She has traveled all the way from Houston. It's a long trip, but that is nothing compared to the trip of OSIRIS-REx. So if you've been watching the videos, OSIRIS-REx was shot off into space September 2016, intercepted with Asteroid Bennu, collected samples, and dropped them off in September of last year, 2023. And Rachel and her team have been working to get ready for that, collecting those samples and making them, keeping them in good form so that we can study them, so that scientists can study them. And so I'm going to introduce her to share what they've been doing. Rachel?
Thank you, Jennifer. Okay. Hello, my name is Rachel Funk. I work at Johnson Space Center in Houston, and I work on a number of different projects there, but the main one that I've been focusing on in the last couple of years has been OSIRIS-REx. So, thank you guys for coming. I'm very happy to be here. I have a soft spot for, I don't know what happened. You're good. Okay. I have a soft spot for community colleges. I started off going to a community college. I went to Lone Star Community College in Tomball, and so I didn't go to college right out of high school. I went about 7 years after I graduated from high school. I waited tables, and I bartended, and I painted walls, and I, gardened, and I did babysitting and all sorts of different jobs until I finally decided, you know what? I see all my friends going to school. I think I can do that too. And so I started going to school at Lone Star. And I originally was like, I really like science. This is really fun. I like science a lot. And so I was like, I'm going to study biology, and maybe I'll be a doctor. And then I was like, I don't really like blood very much. That's not really my thing. I don't really enjoy that. So I took a geology class, and I had a really great time. We went on a field trip, and I learned all about fossils in Central Texas, and then we had a whole segment about dinosaurs. And my teacher had these toy dinosaurs that he brought, and he, at one point I turned around and he was making them fight each other, and I was like, all right, I think I finally found my people. And so I decided that I was going to go to school for geology. And so after I graduated from Lone Star College, and also while I was at Lone Star, I decided that, I should probably get involved while I was there. So I joined this organization called the Eco Club, and it was fun. We basically, we planted trees with kids on Earth Day. We cleared trails in national parks, cleaned beaches, things like that. It was a good way to make friends with people that were doing things that I wanted to do, and they were going in directions that I wanted to also go in. And so I didn't know exactly what direction that was yet, but I knew that I wanted to do something better and bigger, and that was a good way to get started. So after I got my Associate of Science from Lone Star College, I went to school at University of Houston main campus, and I started studying geology there. And I joined Geosociety, where we took a lot of field trips, same kind of thing. We would volunteer, do things like that. And I went on a field trip to NASA, and I was like, man, it'd be really cool if I could work here one day. And I didn't really think that I could do it, but I thought maybe, just maybe I could. So, it kind of sparked the idea of what the eventual goal was going to be, and worked out. I'm here, so that turned out really well. So I got my Bachelor's of Geology, Bachelor's of Science in Geology in 2013 from University of Houston, and my senior year, I took a class with a professor that had formerly worked at NASA. And so I started talking to him a lot about Mars, and he knew that I was really interested in Mars, and he liked that because he was really interested in Mars. And so he convinced me to go to grad school, and he was my advisor, and his wife worked at Johnson Space Center. And so she was my external advisor, and she trained me how to use the microprobe on Martian samples there while I was in grad school. And I made a lot of friends while I was there and decided I definitely wanted to work there. And that's what I was gonna do. Without a doubt, I was sure that was what I was gonna do. And so while I was at the University of Houston, I still needed to work. And so I worked as an isotope geochemist. So I did a lot of really difficult lab work while I was there. It was very challenging. It was very kind of dangerous work. You had to work a lot with a blowtorch and with a lot of carcinogenic chemicals and a lot of really dangerous things. So if you didn't pay attention, it could potentially not only ruin your day, but maybe your life. So I knew I didn't want to do that kind of work forever. And I'm like, I'm making all of these contacts. I'm studying Mars for my master's thesis. This is gonna work out, it's gonna work out. So finally, it did work out, and I got my master's degree in geology, actually after I'd gotten hired on at NASA. So my history at NASA is that I was hired on as a meteorite processor in 2015, and then in 2020, I became a small particles processor, which means that I started working with microscopic particles instead of larger rocks. So the collections that I've worked in the Antarctic meteorite collection, and I've worked in the cosmic dust collection, the Hayabusa2 collection, and the OSIRIS-REx collection now. I also work some in the planning for the Mars sample return mission. So this is me currently. I'm the astromaterials processor, as well as the OSIRIS-REx and Hayabusa2 lab manager. And this is my team of processors right here. They're great. I love working with them. I depend on them very much. A little bit of personal about me. Whenever I'm not at work with asteroid samples, I'm probably hanging out with my daughter or my dog. This is my daughter Penelope and my dog Gunther. And Penelope is really into NASA and OSIRIS-REx too. She likes to come to work with me, so we like to go camping a lot, hang out outside. She likes to find things whenever we go camping and save them and then bring them to work, at my work, and look at them in the microscope. So I'm hoping she's going to be a scientist too. Okay, so now I'm going to tell you guys a little bit about like the most incredible story that's ever happened to me. I never in my wildest dreams thought I could get to be a part of something so big and amazing, but mostly I just have a lot of pictures moving forward, so I'm just going to show you guys the pictures and tell you about them. So OSIRIS-REx is an asteroid sample return mission. It went to the asteroid Bennu. OSIRIS-REx stands for Origins, Spectral Interpretation, Resource Identification, and Security Regolith Explorer. It launched in September in 2016 from Cape Canaveral in Florida. So some important dates here are it arrived at the asteroid Bennu in December of 2018, and it surveyed the asteroid for a bit, and then it actually collected sample in October of 2020. And fun fact, I don't know if anybody has read about this or not, but Brian May from Queen actually helped and was a member of the science team and helped us choose the location that was sampled on the asteroid. So we like to think that's pretty cool. So in April 2021, that was the last flyover of Bennu. And then in May of 2021, OSIRIS-REx began its journey back to Earth. So in 2020, whenever I began my job as a processor for OSIRIS-REx, some of our goals, and I'm sure that I'm missing some of them, but some of the main ones were for us to create a lab at Johnson Space Center to house the samples for safekeeping and processing. We needed to create a temporary clean room at the Utah Testing and Training Range for the receival of these samples whenever they returned to Earth, because they were going to actually land in Utah at the military base, and so we needed a place to put them as soon as it hit the ground. We needed to be able to monitor that lab space and the temporary clean room for potential contaminants. We needed to develop a procedure to open the flight hardware and how we were going to safely extract the samples, and we had to practice those procedures and make sure that it came like second nature to us whenever we were doing our operations to get the samples out. We had to develop a plan to safely contain and store those samples once we got them out. We had to develop sample handling and lab procedures and protocols for this sample collection. We had to develop a database to keep track of the samples and the hardware. And then we had to develop hardware to support all of the above, which brought us to having our very first engineering team brought into Curation. So that was really exciting. We had never had engineers work with us before in sample curation, and having a team of engineers work with us was really critical in us being able to safely open up the hardware and get the samples out so that everything was done the right way in a timely manner. So this is our team. This is the Curation team. It's pretty incredible whenever you realize how much work has happened in the last 2 years, and it's just these people, for the most part, that did it. And so they're pretty great. This right here is Nicole Lunning, and she is our lead curator. Oh, sorry. So she's kind of like the boss of the group. She does an amazing job. Okay, so in 2020, whenever we first started, we knew we needed a lab space for the samples, and so this is kind of our first initial drawing whenever we started coming up with a plan and talking about it was we came up with these drawings for the lab, and then construction began on the lab in 2020, and then immediately COVID started happening. And so everybody got sent home, and so it was a big challenge for us to have the labs completed in a timely manner with COVID, because we had a lot of shortages for supplies, and it was difficult to get the right people on site at the right time to check work and verify that things were being done correctly. And so getting this lab completed was a major undertaking, but we got it done, so that's great. Outfitting the lab was another challenge because of all of the shortage issues that we faced due to the pandemic. I won't go through this, but this is just kind of a list of all the different items that we had to find and get into the labs and get set up before the samples returned in 2023. This is a picture inside of the OSIRIS-REx lab as it was being completed, and this is in what we call our TAG-SAM glove box, and they're putting a piece of special glass onto the outside of that glove box, and you can see how thick that glass is. And so all of the work that we do, we have to look at the samples through that thickness of glass to see the samples and figure out what's going on. But we put special glass on there so that our imaging people requested this type of glass in our glove boxes. So this is a picture looking into the OSIRIS-REx lab in Houston from our thin section lab. And so this is the lab completed, and you're looking directly at what we call our TAG-SAM glove box, and then behind that there's a larger glove box that we call our canister glove box. And so this is where all of the samples from OSIRIS-REx are now currently living, with the exception of some samples that we have already sent out to our science team members for studying. So these are images of our temporary clean room in Utah that we built. This was built inside of a hangar and a military base at the Utah Testing and Training Range. And the sample landed here and was picked up in a big harness by a helicopter and then brought to this temporary clean room. And this is me right here, and I'm working on setting up some contamination testing before the actual return of OSIRIS-REx. And then this picture on the bottom is during construction of the temporary clean room. And then the above picture was taken maybe about 2 hours after OSIRIS-REx landed, and we're looking at the hardware as we're starting to take the capsule apart. And so Johnson Space Center was there with 3 members inside of this clean room, alongside with Lockheed Martin, who also had 3 members. And so they had 2 spacecraft technicians that were there to take the flight hardware apart because it was still under their custody at that time. But Johnson Space Center was there to document all of that flight hardware as it was coming off. So that's me with my pink gloves right there pointing at it. So that was a fun day. It was a long time in the lab though. We didn't know how long we would be in there documenting flight hardware, and we were in there for about 8.5 hours with no breaks for food or water or bathroom or anything. So I don't know how we got through that, but it went by a lot faster than I thought it would, in my mind. This is inside of the temporary clean room, and I'm doing some contamination control testing. And so this is an organic wafer. And so I leave these wafers out for 24 hours, and then they're analyzed for how many particles are on those wafers. And then right here is an air sampler, and it's an organic air sampler And it's a little tube that you run for 6 hours, and then you analyze for particles in the air. These are some pictures of us practicing for how we were figuring out how to develop our procedures for dissecting the flight hardware whenever the OSIRIS-REx capsule returned to Earth. So we had to develop a plan on how to open it, but we had to open it safely so that nobody touched the samples whenever we opened the flight hardware. We didn't want to drop screws in the sample. We didn't want to shed any metal particles. We didn't want to shed any skin particles. And so we had to come up with a very, very careful plan to do that. And so part of that plan was that all of the work that we were going to do was going to happen inside of a nitrogen glove box. So we built these, what we called mock-up glove boxes to practice in. And at first we didn't use gloves, we just made the boxes. And then eventually we started using gloves as well to practice. But the actual glove is a pressurized nitrogen, glove box is a nitrogen pressurized glove box that we use. But we practiced for about 2 years. We would just practice over and over and over again. And anytime someone had an issue or they moved their hand a weird way, we would stop and talk about it. And it almost seemed ridiculous, some of the things that we would talk about. I mean, one time I had, I think, an hour-long meeting about why, in the video footage, I was sweating in one of the rehearsals. Like, why is your lip sweating, Rachel? Why are you sweating while you're doing this poor movement? You're not supposed to sweat because we don't want you to drop it and we don't want you to be nervous. So they wanted to get to the root of why I was nervous in that moment. And it was, because the mission PI was in the room at the time and he was crowding our space and he was looking over our shoulder. And so it ended up with a rule that he was not allowed to step within like however many feet of any of the processors while they were working. But so, I mean, it seems very ridiculous and tedious, but it's very important that nobody drops the sample, because if you think about it, the mission cost over $1 billion. So you look at that kind of as a comparative for what that sample is worth and the time and the effort and the money that went into getting it. So it's very, very valuable. So you want to be very well rehearsed in everything that you do to handle the sample. This is another rehearsal that we did. We developed procedures for how we would collect environmental samples whenever this is like a mock-up of the sample canister after it landed on the ground. And this is not the real thing. This is one that we did in Denver, actually, with Lockheed Martin. And this was to develop a procedure for collecting environmental samples so that we would have comparable samples, so that if somebody found something weird in the asteroid sample, we could say, oh, look at the dust that it landed into and make sure it wasn't something that was also in that sample. And so we also had to be very careful when collecting the environmental samples, because the sample canister landed at a testing range, and so there are like live munitions in the ground, and so we had to have specialized people there from the military that would go and check the area first and flag it off, and you could only walk in certain flagged areas when they told you that you could. And so it was a little bit nerve-wracking to, just make sure that you were following what they were saying to do exactly to a T, because that this is an area that they test bombs in. So you want to make sure you don't step on one of those by accident. Part of what we also had to do was container development for the samples. And so these are some images of some containers that our engineering team developed. Over on the left side is what we call our TAGSAM transfer container. And so once we dissected the sample canister down to just the TAGSAM, which was the actual collection head, the part that collected the sample of the asteroid, once we got it out of the capsule, like the capsule is the part that it kind of travels in. Once we got it out of that part, we wanted to get the tag SAM into a cleaner environment, so we put it into the tag SAM transfer container to move it into the tag SAM glove box because it didn't have all of the charred debris from the sample capsule on the outside of it. So once we started getting to where the bulk of the asteroid sample was, we had it in a much cleaner, nicer environment by then. And then over here, these are our containers that we put our samples in as we've been subdividing samples, and you can see there's a little grain inside of it, and that's a sample that went out to actually the Space Center Houston. That is their public display sample. So we had to develop our sample handling procedures as well. We used a simulant called Tagish Lake, and we also worked in our mock-up glove boxes. And so on the left, that's me, and I'm playing with some simulant and trying to figure out how to carefully pick up one of those trays without letting any of the particles move, and also not touching any of the particles with one of those bulky gloves. And so it's very important to us so that we keep those trays very still, and that way whenever our science team is looking at the images of the trays, they can choose which pieces and particles they want from the tray. So we go back and use those images like a puzzle to find the pieces that they want. So we have to be very, very careful whenever we pick up and move the sample around. We had to develop a database for keeping track of the samples that we have as we start subdividing the sample, and we pulled it out of the tag SAM head and we started distributing it around the world. And so you can kind of see there's a lot of detail that we keep track of. We keep track of the weight of the sample, we keep track of sample descriptions as we start to break them apart. As we're collecting a sample, if there's something odd about that, if there's some adhesive that we think we see going into the sample, we'll make note of that. So we can keep a very good record of everything that has happened to each grain of the sample as soon as it's gotten into our custody. This is from our hardware development. Our hardware team developed a lot of containment systems, as you saw before, but they also developed a lot of hardware for us to get the sample out, including a baffle and tray system that we ended up pouring our samples into so that we could take good images of the sample. And so this is our lead engineer, Sal, and on the bottom of the baffle system, he decided to autograph it, and he had it say, "Welcome, Bennu," from the JSC Curation team, and he put all of our initials on it, so that was pretty cool. Okay, so that was all of the planning, and this is kind of what actually happened. This is an animation showing the OSIRIS-REx spacecraft as it's rendezvousing with Earth, and it's going to release the SRC, or the sample return canister is the SRC. It's going to release it, and it uses thrusters to direct itself into the Earth's atmosphere, and then it's shot into the Utah desert, and I was told that it was like shooting a bullseye from across a basketball court. So that's pretty cool that they were able to make that target landing exactly the way that they wanted to. So this is an animation of it entering the Earth's atmosphere. It was visible. If you were in the Utah area at that time, it would have looked like a shooting star. This is it parachuting into the desert. This is an image of the SRC after it landed on the desert floor. You can see that it's all black and charred, and that's from getting burnt up upon entry into the atmosphere. These are the science team members as they are taking the environmental samples around the SRC before the SRC is collected and taken to the temporary clean room. And so these are the spacecraft technicians here, and they are packing it up, and they are going to hook it up to the helicopter and bring it to the temporary clean room at the hangar inside at UTTR. This is an image of it strapped up to the helicopter. And this is the helicopter about to drop the SRC off at the hangar. And so the hangar, the clean room is located inside of this hangar here. And whenever we were there, there was a coyote in the parking lot that was kind of following us around the whole time. And we were like, I don't know, he was like our mascot of return. We called him the Dugway Coyote because Dugway was the name of the area we were staying. So this is a picture of the SRC being brought into the hangar, and that's the doors of the temporary clean room. And these are members of the curation team bringing it in. This is the SRC once it was brought into the temporary clean room. The main goal of being in the temporary clean room was to hurry up and get the sample onto a nitrogen purge because the samples were exposed to oxygen from the time it entered the atmosphere until we got it onto a nitrogen purge. So it was exposed to oxygen for about 2 hours. And so it was our goal to get it on a purge as quickly as possible and to start taking off some of the outer hardware, like that charred sample lid and bottom, the capsule. And so Lockheed was taking things apart, and NASA was there to document as Lockheed was taking it apart, and each side also had a photographer. After we got it on purge and got it packaged up, we got to put it in this big silver box here on the military plane. I believe it was a C-17 that we got to go on. And so the critical staff got to fly with the sample from the military base to Ellington Field in Houston. And then we had a caravan pick us up to drive us to Johnson Space Center with the samples. So we flew to Houston from Utah. This is the sample being brought into Johnson Space Center, into our facilities there. This is our canister glove box, and so we wheeled it upstairs and into this lab, and we brought it into the canister glove box. And then we opened up the canister lid, and this is whenever we discovered that there was a lot of extra sample outside of the tag SAM. So this here is the tag SAM. This is the part that collected the sample, and you can see there's sample all inside of the canister lid and outside of it. So it was just spilling over, so that was great news for us. And so this is us right after we opened it and realized that we had so much sample, and I think probably all 4 of us are crying in that picture. And so this is a picture showing the extra sample inside of the canister. And so this is a nice image showing the tag SAM here, and this is the canister lid that kind of is like a clamshell, and it's got a sample all around it. So this kind of slowed us down a little bit in our plan because we had to stop and document and collect all of that sample. And so this is a picture just showing how we collect sample. We take a lot of pictures and we work together. Your mobility is very strictly limited in a glove box, and also your hearing, because the fan filter units are very loud inside the lab. So we work together very closely, and we rely on a lot of nonverbal communication with each other. And as you can see, there's one person over here with kind of like a dustpan, and there's one person here that's scraping sample into the dustpan across from him. And I guarantee these guys can't hear each other talk. And so that's kind of how we work together. And so we have a very well-selected team for this type of work. It takes a very calm and cool person, and we all have to work together really well and be on the same page. And so it's been an amazing team to work with. And so after we collected all of the sample that had spilled out on the exterior, we had to flip the sample over to start working with getting the tag SAM opened up. So the first thing we had to do was to get it separated from what we call the avionics deck. And so to do that, we had to flip it, and it was a 4-person operation, and we were very nervous because we were flipping all of the sample over at once. We didn't want to spill it, so this is a picture of us doing that operation. And then after we flipped it over, we put it into the tag SAM transfer container, and then we moved it into the tag SAM glove box. And so this is a picture of them loading it into the airlock on that glove box. And this is a picture of the container inside of the glove box. Everything's very shiny. It's kind of hard to get good images with all of the reflections, and so here is a picture after we had already started taking things apart. Is a Mylar flap, and the rest of the sample is underneath that Mylar flap. So we're working diligently on taking out all of the 35 screws that we need to take out to get to the sample, and these are called contact pads that interfaced with the surface of the asteroid whenever the tag SAM punched into the surface of the asteroid, and we are documenting and removing those contact pads. And then we got to this configuration, and we needed to remove 2 of these screws on the outside here, not all of them, because only 2 of them actually were interfacing with another surface at that time. And then we had to get these 6. So we had taken out 28 of 35 screws. And whenever I went to get one of these screws, I can't remember which one, but it was 2 opposite ones. We'll say it was this one. I went to turn it, and the bit just basically melted in my hand, and it broke the tip off. And basically the metal that the screw was made out of, the tag SAM was made by Lockheed Martin. We didn't know exactly everything that everything was made out of, and so our tool that we had to open the screws was too soft, and it was made out of the metal that was allowed inside of our glove box. And so basically we were halted in our procedure, and it was very upsetting because I had a bit in my garage that would have done the job, but we got a red light, and we had to develop a tool that could take out the screws and a material that was allowed inside of our glove box. And so we are very, very cautious about the materials that we allowed to interact with our samples, because we only let certain materials interact with samples, because those materials have been the same materials that have interacted with samples since the Apollo samples came back in the 60s. And so the community is very well aware of these types of metals that we use, and we don't venture outside of those metals often. And so the metal that we could use to make a new tool that would get the offending screws opened was called Biodur 108, was the alloy, and it's a medical stainless steel, and it's very rare, and it's very expensive, and it's not easy to get your hands on. And we needed a custom tool to get the screw out. So our engineering team developed a tool in probably about a week and a half, and then it took us a few months to get the tool made in that alloy. And so, let's see. Oh, in the meantime, the science team was chomping at the bit for sample because we didn't have the tag SAM open all the way, and the mission requirement was 60 grams. So what we decided to do as processors was very, very carefully, we had one processor hold a flashlight along the side so that we could look into the screen and see where sample was through the side, the shadows. And then we had another processor hold a tool down on this Mylar flap so that you could access the sample inside. And then another processor went in and basically scooped it out like breakfast cereal and very, very cautiously put it into containers. And we scooped it out until we had scooped about 70 grams out that way. And the mission requirement was 60 grams. So at that point, even though we hadn't gotten access to all of the sample, we had met our mission requirement. The science team was happy, and everybody would back off so we could figure out a plan to open the rest of the container and get it out. So once we got the sample opened out, this is a picture of all of the rest of the asteroid sample inside of the tag SAM head before we poured it into our baffle system. Oh, and this probably should have gone before that picture, but this is a picture of the team whenever we use the special tool to open up the canister. This is one of our engineers, Naftali, and he's holding the special tool. And this is the team after they opened it, and then this is some of us up in the thin section lab watching them get the screw open. And so once they got that screw open, we could go ahead and proceed with our plan of opening the rest of the sample. So that was a very big day for us. We were very, very happy. And so we have, this is the rest of the sample on the base plate of the tag SAM. We had removed everything else off of the tag SAM, and the only thing left to do was to just get that sample off of that plate. And so we were going to pour it onto this baffle system that's underneath, and it has 8 trays underneath that we want the sample to be divided into so that it is kind of divided out well for imaging purposes, is why we kind of came up with this plan. And so this is a picture of us and how we poured the sample. And so Julia and I stood across from each other, and we lifted, and then we poured, and we would call directions as we poured the sample into the trays. And then Janitul on the far right was there to help give us a hand to get the plate onto a stand there after we were finished. So everything that you do in the glove box is a multi-person operation. And so you kind of have to discuss everything that you're going to do beforehand, because you can't really hear each other in the lab. It's really loud in there. And you use a lot of just your eyes to figure out what the other person is saying and what they're going to do. So it's weird. We're kind of like a cult. Like, we're very close with each other. We all hang out outside of work a lot too. Usually you want to get away from your coworkers whenever it's over, but we don't. We all hang out a lot, and we're all really great friends. And so this is after we had poured the sample off of the plate. You could see there's a bunch of it still stuck to that plate, but we poured it into the tray system, and we're kind of sweeping the rest of the sample down into the tray system. And this is a close-up of how we sweep it into the tray system. This is our tray system after we had poured it. This is just a picture for fun. This is Rex, and this is our mascot for OSIRIS-REx. She is a stuffed penguin in a T-Rex costume, and we stole her from Lockheed Martin. It was a heist, and so whenever Lockheed Martin comes to visit, we make sure to put her on display in a window behind a coded door so that they can see her, but they can't get her. And so she has a whole wardrobe. You know, she's got formal clothes. She's got a clean room bunny suit so that she can go into the lab. And so that's just for fun. And then this is a fun picture that I got to do with the engineering lead. This is some of the hardware that his team designed. That's the tag SAM transfer container. So that was kind of a fun, dramatic photo shoot that we got to do for OSIRIS-REx. But anyway, that's it. And if anybody has any questions, I'm happy to take them.
So I'm kind of curious, like, how do you get into a field like this? Like, what degrees do you need to even do something like this?
So I studied geology, and we have a lot of different fields. I took a lot of math. I know this is a math group, so a lot of math goes into this. We have a lot of engineers, so we even have a geneticist. that has really great microscope experience, so she's perfect for what we need. We have a physics person, we have an astronomer, so any different type of science or engineering or math type of background can get you here. And you know, I learned a lot about geology, and my school at University of Houston was very heavily like oil and gas. And so whenever I graduated with my master's, I knew so much about oil and gas and, you know, geochemistry for that. And I learned everything I needed to know about my job at my job. And so now I'm kind of a jack of all trades. I'm a geologist, but also I know how to design labs. I know how to outfit a lab. I know how to, you know, collect an asteroid sample from a desert now. I can, you know, build a database. So, you know, any type of job that you get, you can learn a lot of different things. So if you go into like any type of math or science or engineering type of field, you can kind of get your foot in the door.
I'm just curious what oxygen would do to the sample.
So oxygen would probably rust out the sample. We want to make sure that it does not experience interaction with oxygen. We're trying to stop that. So it did interact with oxygen for about 2 hours, but we try to stop that. And so we monitor that. We actually have a volatile trap attached to our glove box to make sure that there is no oxygen getting into the sample from this point forward as soon as it got into our custody. But it would start to rust out the sample, and we're not exactly sure what it would do to the sample. We know that it would change it probably very drastically. And especially the water in Houston, humidity, it would be very, very bad, because that's something we're looking for in the sample, is we're looking for water. And so we don't want to introduce that into the sample.
What about if you get close to the whatever you collect from the outside, it is danger for you, or is...
We do not expect that this sample would be dangerous to us. And so while we are looking for things that would be like the ingredients for life, this sample the asteroid doesn't have an atmosphere, and so it's been so irradiated by the sun that we wouldn't expect that there would be like any type of a living virus or something along those lines that would be dangerous for humans. And also we have a variety of other astromaterials samples and different collections that we've been collecting since the 60s. And so we've never seen anything harmful or dangerous to humans in those samples. So that's also another reason why we don't expect to find anything. But for the Mars sample return collection, we are being very, very cautious about that collection and potentially bringing something home that would be dangerous.
Is there a reason why there isn't a radio system in place when you're working with the glove box so you can communicate with one another over the fans?
We do actually communicate a lot with earbuds. So we'll have somebody, usually we'll have a lead, we always have somebody that's leading, whether it be myself or Nicole, the curator. We'll tag team, one of us is in there leading. And we are kind of in charge of making sure that we have the procedure being followed and we have the list of kind of what's happening. But whenever you're working in the glove box, your hands are here. So, I mean, you could put on a headset, but the problem is that it's the materials compliance issues. And so we're very, very weird about what you're allowed to have. And so we're not allowed to have certain different materials in the lab. So whatever's on the speakers and things like that, it just depends. I mean, we might be able to find something that we are allowed to use, but so far, the only thing that our curator has approved has been earbuds and cell phones. Yeah, so we kind of rely on that a little bit, but it's usually the person that's leading has the earbud and they're communicating with somebody that's sitting outside the lab. And then also the curator, who is kind of the person who makes these calls, she's very concerned about people having access to startle you whenever you have your hands on the samples. So in a way, I think it's kind of, maybe she doesn't want someone in your ear being like, hey, stop that, or do this, and you have a sample in your hand and it might, make you spill it or something along those lines. It's a good question.
So the asteroid might be like moving so fast, so it has a high temperature on it. So the sample you collected, was it more like a metal thing or a rock thing?
So it's basically a rock sample. It's a lot of dust and rock, and so Bennu is what we call a rubble pile. And so it's a lot of rock and dirt and rubble that is loosely condensed together, but it's not as condensed as the Earth is, where it's differentiated into different layers, where you have the crust and the mantle and the core. It's not like that. It's just a bunch of things like all jumbled up and smushed together, but not fully condensed together yet. And so it is rock, and it's very kind of like black rock, and it has kind of like a salt and peppery look to it. It's mostly black, but whenever we like to turn off the lights and then shine flashlights on it so you can really see all the sparkles and the glitter and how pretty it is, and you can see a lot of like lighter particles inside of it as well.
So I was wondering, like, what is it like working with your team compared to working with like the engineers and the people on the hardware side?
It's great. We have really worked together as a team well. Our engineers like to, joke about how they could be processors, and then our processors like to joke about how they could be engineers. And we really overlap with each other a lot because, sometimes the engineers will be in the lab and they'll be helping us assemble a container in the lab, and then something will happen with the canister and their sample over there, and it's a heavy piece of hardware, and maybe I could call another processor to help me in there, but it's going to take that other processor at least 20-30 minutes to get suited up and come in the lab. I could just ask the engineer that's standing right there to help me. He's been capable of doing everything else, so I'm just going to ask him to help me with the sample, and vice versa. If he has an engineering issue, he's not going to wait for his buddy, he's going to ask the processor. So that's been great. We overlap really well together, and honestly, the engineers have spoiled us as processors because the whole time we've been developing our procedure, the engineers are following us around with their iPads, and they're like, what can we do to make your job easier? What kind of device could make this better for you? And I'm just like, wow, I have so much attention. This is amazing. And so they have really spoiled us and made our jobs a lot better and easier. And so incorporating the engineering group into the curation team has just been amazing and very critical to our success.
How heavy is the actual sample, and what is the future of OSIRIS-REx?
So we have collected, it's just over 121 grams, and for reference, that is about a coffee cup full of sample, which is the largest asteroid sample collection ever collected. The first one was JAXA. They collected some sample for Hayabusa, and then Hayabusa2. So they had 2 asteroid sample collection missions, and then OSIRIS-REx was the first American one, and we collected a coffee cup full. 121, I think it's 121.6, but don't quote me on that.
Over here, Rachel.
Hi.
What made you want to do this?
Oh, go into geology or go into space? Or both?
Both.
So I wanted to go into geology because whenever I was a kid, I would go outside and play, and I always wanted to understand everything around me and the earth and why things happened. And I really liked mountains, and I wanted to know how they got there, and I liked being outside and camping. And so that's what kind of got me interested in geology. And then whenever I started studying geology, I met that teacher that I had that had worked for NASA, and he started talking to me about volcanoes on Mars, and that I could study that and do that for my job, and I was just blown away by that. I couldn't believe that that was even a real thing that someone could do. And he really encouraged me, and he worked with me, and he told me that I could do it, and he introduced me to a lot of the right people. And I, as soon as someone told me that I could look at, basically, a meteorite, if you think about it, it's the leftover bits of a shooting star. So if you have the chance to look at that, that's amazing. And if somebody wants to pay you to do that, that's even more amazing. And so if you got the chance to do that, that's something that you don't walk away from. It's a good question. Thank you.
I was just curious, were there any other problems or close calls besides the screws or kind of things that y'all were looking out for during the processing of the sample?
Yes. So there are a lot of things that we were looking out for. So a lot of the work that we were doing, we call contingency work. And so a lot of the supplies and planning that we were doing was to basically prepare for the very real possibility that the capsule could have crashed and the sample could have been all over the desert floor. And so we could have been out there for, weeks collecting it that way. And so a big part of my job was to prepare for that to happen and to have all of the supplies in order and documented and organized and laid out and have teams laid out and organized in times and shifts that they would go out to sample collect from the curation team. So, that was a big part of it, was basically we were preparing for what we call a hard landing. It's a very polite word for a crash. But so we had a lot of contingency plans for that. And then as for the processing end of it, we were just concerned a lot about, just any fastener or screw not budging. We were concerned about that. I did have a little bit of concern about the metals, because whenever we had done our rehearsals, the soft metal of our tools was getting chewed up whenever we were trying to do it, but it always opened everything. It always worked and it got everything open. So I didn't think it would be as bad as it was, but I was a little bit concerned about that. So the tools being soft, we were concerned about that. We're always very concerned about dropping sample. That's probably, as a processor, that's like your number one concern, and you really don't want to do it ever, but you really don't want to do it whenever everybody's watching. And so, if it happens, like, we're all human, we're not robots, and eventually it does happen to everyone, and you're not going to get fired. You just take good pictures and you document it and you take note of what happened, is the process that you would go through. But for OSIRIS-REx, there was really a lot of pressure on our team. We had live cameras on the glove boxes on our hands, like close-up of our hands of every move that we were doing for preliminary examination for, a couple of months, and that was extremely stressful. But yeah, dropping samples, things getting stuck and breaking, dropping a screw inside of the sample, or a crash were the biggest concerns for sure.
What is the research you're trying to find on the sample, and what are you wanting to do with the information that you find from it?
That's a very good question, and so a lot of that can be answered in the name of the mission. So for origins, we are looking for the ingredients to life in this sample, and a little bit about that I'll say. I just went to the Lunar and Planetary Science Conference last week, and I saw the preliminary results from the sample, and someone has preliminary results, not final. They found 3 out of the 4 DNA bases in the sample. And so they are looking at the sample for ingredients for life. They're looking at the sample because it is a near-Earth asteroid. It has the potential to collide with Earth in a very, very long time from now. So we like to look at asteroids of that nature so that we can prevent them from crashing into us eventually. That's not a major concern with this asteroid, so don't be alarmed. But we like to look at that. For that, we're also looking for potential resources on this asteroid that maybe we could use for ourselves. And so there are a lot of valuable reasons to look at, especially carbonaceous asteroids. Okay.
What does the future look like for these kinds of projects?
It looks good. I mean, the next thing that's coming up is Artemis. And so that's a very exciting one. They just launched to go to the moon now, and then they're going to send astronauts there. The Mars project, I don't know if you've seen much on the news about that, but it's not looking as good currently. But I feel like it's got time to recover. Usually just depends on who's in charge at the moment and what their personal, kind of goal is. It seemed like in one administration, it was very heavily centered on Mars, and then it was very much geared towards the moon. And then now we're definitely heavily centered on the moon right now, but not so much on Mars, but I'm hoping it goes back. We'll see.
And our last question.
So you were talking about the 3 markers that were found and the preliminary results. Are you allowed to comment on any of those constituents and what they were?
I would not feel comfortable commenting on it, but I would definitely recommend Googling it and just looking it up, because I would try to find the abstract. Just search LPSC, the Woodlands 2024, and then DNA markers, and see if you can find something, because this was very much like I was looking at an email while I'm in a talk, and I heard it said, and then I looked up and I was like, oh, that's awesome. And then I went back to my email. So please, definitely look it up and verify this information.
Thank you so much. I'd like to invite Dean Bowling up just to say a few things.
All right. Hi, everyone. Thank you so much for hanging in there with us for this evening's talk. It was so interesting to see all of the many steps that it took to look at some samples of particles. I kind of wish I could touch them myself, but it looks like it's a whole process. So I want to thank you all for coming out. Truly, the purpose of this event really has been to inform our students of all of the many, many diverse careers out there that are touched in some way by STEM. I hope that you found something interesting, and I hope it piqued your interest so much that you're looking to shift your major to geology or mathematics, right? Or biology, that's what I taught. But special thanks to the team who worked really hard putting this on. This is the first time we've had an event in this space. I think it worked rather well. We probably have taken some notes on some things to do next time, but I really appreciate you guys. We know coming up on a school night, might be difficult, but we do appreciate you. And we have a special gift for our speaker, Rachel. So I want to say thank you so much for coming, a very small token. And then I'm going to pass things back off to Jennifer. Thank you, guys.